13.8 billion years ago, something impossible happened. The entire universe exploded from a space smaller than an atom, bringing time, matter, and reality itself into existence. But here's the shock. Scientists now know the Big Bang wasn't the beginning. Before that cosmic fireball, there was something stranger than empty space. There was a quantum void buzzing with invisible energy, a place where the laws of physics themselves were being written. We're about to journey through colliding dimensions, endless cycles of creation, and discover why nothing might be the most powerful force in existence. If you're ready to see how reality bootstrapped itself from the impossible, hit that like button and subscribe. Let's dive in. Picture the darkest corner of space you can imagine. No stars, no planets, no light, just emptiness stretching forever. Now, here's what scientists discovered: that emptiness is a lie. When physicists examined the vacuum of space using quantum mechanics, they found something shocking. Empty space isn't empty at all. It's seething with energy. Think about the ocean's surface on a windless day. From far away, it looks smooth and still. Move closer, and you'll see tiny ripples, random disturbances appearing and vanishing. The quantum vacuum behaves the same way, except these ripples are invisible fields of energy that exist everywhere, all the time. This discovery is confirmed science, proven in laboratories across the world. The vacuum carries what physicists call zero-point energy, ZA, the lowest possible energy state that still contains measurable power. You can't remove it. You can't turn it off. It's woven into the fabric of reality itself. Here's where it gets stranger. This energy doesn't just sit there doing nothing. It shapes the universe. When two metal plates are placed extremely close together in a vacuum, they get pushed toward each other by this invisible force. Scientists call this the Casimir effect, and it's been measured with precision. The vacuum between the plates has less energy than the vacuum outside them, creating an imbalance that generates real physical pressure. This means that what we call nothing has structure. It has properties. It can be measured, manipulated, and studied. Ancient Greek philosophers believed that if you removed all matter from a space, you'd have true nothingness. They were wrong. Modern physics forbids it. The implications shake our understanding of existence. If the vacuum has energy, then nowhere in the cosmos is truly empty. Every cubic inch of space contains this baseline hum of quantum activity. When you wave your hand through the air, you're moving through an ocean of invisible energy that existed before the first star ignited and will persist after the last one dies. But measuring this energy created a problem that haunts physicists to this day. When they calculated how much energy the vacuum should contain based on quantum mechanics, the numbers exploded. The predicted value came out 120 orders of magnitude larger than what we observe. Imagine predicting someone weighs 10 pounds, then discovering they actually weigh less than a single atom. The gap is that enormous. This crisis tells us something profound. We don't fully understand what nothing really is. The vacuum hides secrets that could explain the birth of everything. Scientists confirmed that empty space carries energy, but the mystery of why it carries exactly the amount it does remains unsolved. What happens when this quantum foam gets disturbed? The quantum vacuum doesn't just hold energy, it creates matter. Right now, in the space between your eyes and this screen, particles are appearing from nowhere. They exist for a fraction of a second, then vanish back into the void. Scientists call them virtual particles, and their existence has been confirmed through experiments that measure their effects with stunning accuracy. Here's how they work. Energy and matter are interchangeable, as Einstein showed us. The vacuum contains energy, and that energy constantly fluctuates. For the briefest instant, a fluctuation can become massive enough to split into a particle and its antimatter twin, an electron and a positron, for example. These pairs erupt into existence, live for a time span shorter than you can comprehend, then collide and annihilate each other. The energy returns to the vacuum. The cycle repeats endlessly. This happens trillions upon trillions of times every second in every cubic inch of space. The vacuum is not calm. It's a furious storm of creation and destruction happening at scales far below anything we can see directly. Yet we know these virtual particles are real because they leave fingerprints. In the 1940s, physicists noticed something odd about hydrogen atoms. The energy levels of electrons orbiting the nucleus didn't quite match predictions. The discrepancy was tiny, but it was there. After intense investigation, they realized virtual particles were responsible. These ghost particles briefly interact with the electron, shifting its energy by a measurable amount. Scientists call this the Lamb shift, and it proved that the vacuum isn't passive. It's alive with quantum activity. The evidence gets even more convincing. Virtual photons, particles of light that blink in and out of existence, create a phenomenon called vacuum polarization. They briefly screen the electric charge of particles, affecting how forces behave at quantum scales. Without virtual particles, the mathematics of quantum physics would collapse. They're not optional, they're fundamental. Think about what this means for the question of nothing. If the vacuum spontaneously creates matter, even for microseconds, then absolute nothingness is impossible. Nature won't allow it. The universe has a baseline level of chaos built into its foundation. But here's the unsettling part. If virtual particles can appear from the vacuum for tiny fractions of time, what stops a bigger fluctuation from happening? What prevents the vacuum from creating something that doesn't disappear? Something permanent? The answer involves a principle that makes nothing even stranger than you imagine. In 1927, a German physicist named Werner Heisenberg discovered a rule that breaks our common sense understanding of reality. It states that you cannot know both the exact position and exact momentum of a particle at the same time. The more precisely you measure one, the less you know about the other. This isn't a limit of our instruments. It's a fundamental property of nature. The universe itself doesn't allow certain information to exist simultaneously. Now apply this to energy and time. The uncertainty principle also states that energy can fluctuate wildly as long as it happens fast enough. The shorter the time interval, the larger the energy fluctuation that's permitted. This is why virtual particles exist. The vacuum borrows energy to create them, then returns it so quickly that the universe's accounting books balance out. Here's the crucial insight confirmed by decades of experiments. The uncertainty principle guarantees that the vacuum can never be completely still. There will always be fluctuations. Always. You cannot have a state of perfect nothingness, because that would require knowing the exact energy at an exact time, which nature forbids. Imagine trying to photograph a hummingbird's wings mid-flight. Your camera captures a blur because the wings move too fast. The quantum vacuum is similar, except instead of motion blur, you get energy blur. The vacuum fizzes with possibilities that never quite settle into stillness. This has staggering implications. Before the universe existed, if there was ever a state of true nothingness, the uncertainty principle would immediately destroy it. Quantum fluctuations would appear, energy would emerge, the void would become unstable. Scientists measure this instability in laboratories. When they cool systems down to temperatures near absolute zero, IMD, the coldest possible temperature, quantum fluctuations become the only motion left. Atoms still jitter, fields still oscillate. You can remove heat, remove particles, remove light, but you cannot remove the quantum uncertainty that makes the vacuum restless. This isn't speculation or philosophical musing. Teams of physicists have detected these fluctuations directly by studying how light behaves in carefully controlled experiments. They've measured the vacuum's random electric fields affecting electrons. They've observed the spontaneous emission of photons from atoms triggered by vacuum fluctuations. The evidence is overwhelming. The uncertainty principle creates a paradox when we think about the origin of everything. If nothing cannot exist because quantum laws prevent it, then something has always existed. Either the universe is eternal, or it emerged from a quantum state that was never truly empty. But there's a third possibility that sounds like science fiction, yet might be confirmed reality. Imagine standing on a frozen lake. The ice looks solid. It feels safe. But beneath the surface, the water is warmer than it should be. The ice exists in an unstable state, waiting for the right trigger to collapse. This is what physicists call a metastable state, something that appears stable but isn't truly at its lowest energy. The vacuum of space might be exactly like that frozen lake. According to quantum field theory, confirmed through particle accelerator experiments, the vacuum can exist in different energy states. There's a true vacuum, the absolute lowest energy possible, and false vacuums that sit at higher energy levels but remain stable for long periods. Our universe might currently exist in a false vacuum, and that terrifies some physicists. Here's why. A false vacuum is metastable. It can suddenly decay into a true vacuum state if the right quantum fluctuation occurs. When that happens, a bubble of true vacuum forms and expands at the speed of light, transforming space itself. Everything caught in the expanding bubble gets restructured. The laws of physics change. Matter as we know it ceases to exist. Sounds catastrophic, but flip the perspective and you get something remarkable. What if the universe itself started as exactly this kind of event? What if, before the Big Bang, there was a false vacuum that decayed into our reality? This theory has mathematical support through something called the Wheeler-DeWitt equation. It describes how quantum states evolve in the context of gravity and cosmology. Scientists in China published work in 2014 showing that solutions to this equation permit a tiny bubble of vacuum to appear spontaneously from quantum fluctuations. Under specific conditions, this bubble doesn't collapse. Instead, it inflates, expands, and creates a universe. The false vacuum that preceded our cosmos would have been incredibly small, smaller than an atom, possibly as tiny as the Planck length, which is 10 to the negative 35 meters. At that scale, space itself becomes grainy and quantum mechanics dominates everything. The usual rules about cause and effect break down. Events can happen without prior causes. Fluctuations can create structure from randomness. This is confirmed physics at quantum scales. We observe it in particle physics experiments constantly. Extrapolating it to the origin of the universe requires a leap, but it's a leap grounded in established science. The metastable false vacuum gives us a picture of pre-bang reality. There was no swirling gas, no primordial matter, no time ticking forward. There was only a quantum state hovering in an unstable configuration, waiting for the fluctuation that would birth everything. How do we know this quantum energy does more than just exist? Energy has weight. It curves space-time, and the vacuum's energy is no exception. Einstein's equations of general relativity tell us that mass and energy both create gravity. A ball of gas creates a gravitational field. So does a beam of light. So does the energy of the vacuum, even though it's spread across empty space. This prediction has been tested and confirmed in multiple ways. The vacuum energy manifests as what Einstein called the cosmological constant, a number that describes how much energy exists in each cubic meter of empty space. For decades, scientists assumed this constant was zero. They were wrong. In 1998, two teams of astronomers made an observation that shocked the physics community. They measured distant supernovae, exploding stars that serve as cosmic distance markers, and discovered something impossible. The expansion of the universe is accelerating. Galaxies are flying apart faster now than they were billions of years ago. Gravity should slow expansion down. Matter attracts matter. The universe should be decelerating, possibly even contracting. But the data showed the opposite. Something was pushing space apart. The only explanation that fits the mathematics is vacuum energy. Empty space carries a small but non-zero amount of energy density, and this energy has a weird property. It creates repulsive gravity. Instead of pulling things together like normal matter, vacuum energy pushes them apart. The more space expands, the more vacuum gets created, which generates more repulsive force. It's a runaway process. Scientists call this mysterious component dark energy, and current measurements show it makes up about 68% of the total energy in the universe. Think about that. More than 2/3 of reality comes from the energy of nothing. Regular matter, stars, planets, gas, everything we can see contributes less than 5%. This discovery transformed cosmology. The vacuum isn't a passive stage where events happen. It's an active participant that shapes cosmic evolution. It bends space-time. It affects the paths of light. It determines whether the universe will expand forever or eventually collapse. The measurements have been refined through multiple satellites and telescope surveys. The Planck satellite mapped temperature fluctuations in the cosmic microwave background and confirmed the amount of dark energy with incredible precision. Ground-based telescopes measured how galaxies cluster and found perfect agreement. Independent methods converge on the same answer. Empty space has power. Real, measurable, universe-shaping power. And this raises a staggering question. If vacuum energy can dominate the entire cosmos today, what could it have done in the first moments of creation? The answer leads us to the most important event that happened before the Big Bang. Everything you've been told about the Big Bang needs updating. The hot, dense fireball that forged atoms and released light across space was not the beginning. It was the aftermath of something else, an event called cosmic inflation. Inflation theory, developed in the early 1980s by physicists including Alan Guth and Andre Linde, describes a period of exponentially fast expansion that occurred before the traditional Big Bang. During inflation, the universe doubled in size repeatedly in an incomprehensibly short time. We're talking about expansion faster than light, faster than anything the laws of physics normally allow. Here's the key point, confirmed through observation. Inflation solves problems that the standard Big Bang cannot. The universe is remarkably uniform. Galaxies separated by billions of light years have the same temperature, the same density, the same properties. How did regions of space that could never have communicated with each other become so similar? The old Big Bang model had no answer. Inflation provides one. If the universe started much smaller than expected, then inflated to enormous size in a fraction of a second, those distant regions were once close enough to reach equilibrium. They were neighbors. Then, inflation stretched them across opposite sides of the observable cosmos. The evidence comes from the cosmic microwave background, ancient light released 380,000 years after the Big Bang. When scientists mapped this radiation across the sky, they found tiny temperature variations that match predictions from inflation with stunning accuracy. The pattern of hot and cold spots looks exactly like what you'd get if quantum fluctuations during inflation were stretched to cosmic scales and imprinted on space itself. But here's what makes inflation revolutionary for understanding before. It happened in a universe that was cold and empty, not hot and dense. The inflationary epoch was driven by vacuum energy, NEHE, the same type of energy we discussed earlier. This vacuum energy caused space to expand exponentially, doubling the universe's size every tiny fraction of a second. Think about a chessboard with pennies doubling on each square. 1 penny, then 2, then 4, then 8. By the 40th square, you'd be a billionaire. Inflation involved at least 80 doublings, possibly hundreds. A region smaller than a grapefruit expanded to a size larger than the observable universe, all in less time than it takes light to cross an atomic nucleus. When inflation ended, the vacuum energy that powered it didn't just disappear, it transformed. The energy dumped into space, creating a flood of particles and radiation. This transformation was the Big Bang. The heat, the density, the primordial soup of matter. All of it came from the decay of the inflationary vacuum. So, the timeline looks like this. First, cold vacuum energy. Then, exponential inflation. Then the energy converts to matter and heat. That's the Big Bang you've heard about. Inflation came before. The question becomes sharper now. Numbers can be deceptive. When scientists say the universe doubled 80 times during inflation, it sounds almost modest. It's not. Each doubling multiplies size by 2. 80 doublings mean multiplying by 2 raised to the 80th power. Write that number out, and you get something with 24 digits. The universe expanded by a factor of 1 septillion, or even more depending on how long inflation lasted. This happened in approximately 10 to the negative 35 seconds, a decimal point followed by 34 zeros, and then a 1. Human minds aren't built to grasp this. Let's try an analogy. Imagine a virus particle, so small you'd need an electron microscope to see it. Inflate it through 80 doublings, and it becomes larger than the entire observable universe. That's the scale of expansion we're discussing. What makes this scientifically credible is that it solves real observed problems. One is called the flatness problem. Space can curve like the surface of a sphere, or curve like a saddle, or be perfectly flat. Measurements show our universe is extraordinarily flat, so flat that if you fired a laser beam across the observable cosmos, it would travel in an almost perfectly straight line for 93 billion light-years. The old Big Bang model couldn't explain this. Tiny deviations from flatness in the early universe should have grown enormous over billions of years. We should live in a universe that curves dramatically. We don't. Inflation solves this by stretching space so much that any initial curvature got smoothed out. It's like inflating a balloon. The surface becomes flatter and flatter as it expands. Another problem is the horizon problem. Light has only had 13.8 billion years to travel since the Big Bang began. That means regions of space separated by more than that distance have never been in contact. Yet, when we measure their properties, they're identical. Same temperature, same expansion rate, same physical laws. How did they coordinate? Inflation answers this. Those distant regions were once close together, in contact, able to reach the same state. Then inflation separated them faster than light could reconnect them. The coordination happened before inflation, and the uniformity we see today is the preserved memory of that earlier contact. The evidence supporting these 80 doublings keeps growing stronger. Satellite missions have mapped the cosmic microwave background with incredible detail. The pattern of fluctuations matches inflation predictions to a precision that stunned researchers. Alternative theories that don't invoke inflation fail to reproduce what we observe. Scientists calculate that inflation must have lasted long enough for at least 80 doublings, possibly thousands more. The exact number remains uncertain because we can only see the effects within our observable universe. Inflation might have stretched space far beyond what we can detect, creating regions forever hidden beyond our cosmic horizon. This means the universe you can see, every galaxy, every star cluster, every bit of light, represents just one tiny patch of a much larger reality. And it all came from a cold, empty vacuum, expanding faster than physics should allow. What powered this impossible expansion? For decades, popular science described the Big Bang as the moment when time, space, and matter sprang into existence from nothing. That picture is outdated. Modern cosmology tells a different story. The Big Bang was not a creation event. It was a transformation. Specifically, it was the moment when the energy driving cosmic inflation converted into matter and radiation, flooding the universe with heat and particles. Think of it as a phase transition, similar to water turning into steam, except far more violent and fundamental. This understanding comes from matching theory to observation. The cosmic microwave background radiation shows us what the universe looked like 380,000 years after the Big Bang. It's a nearly uniform glow with tiny temperature variations. Exactly what you'd expect if the universe was once much hotter and denser, then expanded and cooled. But here's the critical insight. If we trace that expansion backward in time using Einstein's equations, we don't reach a true beginning. We reach a barrier, a point where the physics breaks down because temperatures and densities become too extreme for our current theories to describe accurately. Scientists call this breakdown a singularity, but it's more honest to call it the edge of our knowledge. Inflation changes this picture completely. Instead of time beginning at the singularity, time existed before. During the inflationary phase, the universe was cold and empty, filled only with vacuum energy. Clocks ticked, space expanded, cause and effect operated normally. Then, inflation ended, and that's when the Big Bang happened. The energy that had been locked in the vacuum state during inflation needed to go somewhere. Physical laws require energy to be conserved. So, as inflation stopped, the vacuum energy decayed. It transformed into elementary particles, quarks, electrons, photons, neutrinos. These particles carried enormous kinetic energy, making them move at nearly the speed of light. Their collisions generated heat, lots of heat. Within the first second after this transition, the universe reached temperatures of 10 billion degrees Celsius, hot enough to prevent atoms from forming, hot enough that only the most fundamental particles could exist. This seething plasma of matter and energy is what we call the early Big Bang universe. But that heat wasn't there during inflation. Inflation was cold. The distinction is crucial. The Big Bang wasn't the start, it was the warm-up that came after. Scientists have traced this transition using both theoretical calculations and experimental data. Particle accelerators, like the Large Hadron Collider, recreate the conditions of the early universe by smashing protons together at enormous energies. These experiments confirm how matter behaves at extreme temperatures and validate the equations cosmologists use to model the Big Bang. The timeline now looks clear. First, a cold quantum vacuum. Then, inflation stretches it exponentially. Then, the inflationary energy transforms into heat and particles. That transformation is the Big Bang. After that comes the story you already know: cooling, atom formation, star birth, galaxy assembly. So, when did time actually begin? We're not certain yet. Possibly during inflation, possibly before. The honest answer is that we've pushed the boundary of the unknown backward, but we haven't eliminated it. And the evidence for all this gets even stronger. There's a smoking gun in the data that proves the universe existed before the traditional Big Bang. It's hidden in measurements of the cosmic microwave background, and it's called super-horizon fluctuations. Here's what that means. The cosmic horizon is the maximum distance light could have traveled since the Big Bang began. It sets a limit on how far information can spread through the universe. Regions beyond this horizon have never been in contact with each other. They're causally disconnected. The standard Big Bang model predicts that temperature variations in the cosmic microwave background should only exist on scales smaller than this horizon. Anything larger than the horizon represents regions that never interacted, so they shouldn't show coordinated patterns. But that's not what we observe. The data shows fluctuations on scales larger than the cosmic horizon, much larger. These superhorizon features appear in multiple independent measurements taken by the WMAP satellite, the Planck satellite, and ground-based telescopes. The evidence is undeniable. How do you get coordinated patterns across regions that have never communicated? There's only one explanation. Those regions were in contact before the Big Bang. During inflation, when the universe was tiny and cold, quantum fluctuations occurred across all of space. These fluctuations became the seeds of structure. Then inflation stretched those fluctuations to enormous sizes, far larger than the cosmic horizon. When the Big Bang happened and hot matter filled the universe, these inflated quantum patterns were already imprinted on space. They showed up as temperature variations in the primordial plasma. We see those variations today as hot and cold spots in the cosmic microwave background. The mathematics is precise. Inflation predicts a specific pattern of correlations between temperature and polarization in the cosmic microwave background. It predicts how the size of fluctuations should vary with scale. It predicts the spectrum of these variations should be nearly, but not perfectly, uniform across different sizes. Observations match these predictions with extraordinary accuracy. In 2003, the WMAP team published the first high-precision measurements showing the predicted correlation pattern, including features on superhorizon scales. The non-inflationary Big Bang model predicted something entirely different. The data eliminated the old model and confirmed inflation. 20 years later, with even better instruments, the agreement has only improved. The Planck satellite mapped these fluctuations with such precision that scientists can now test inflation's predictions to fractions of a percent. Every test passes. The superhorizon correlations are exactly where they should be. This represents one of the strongest pieces of evidence in all of cosmology. The patterns we see in the sky could not exist if the Big Bang was the beginning. They require a prior phase, inflation, where the universe was smaller, colder, and governed by different physics. Think about what this means. We've moved beyond philosophical speculation about before the Big Bang. We have observational proof. The light from the ancient universe carries information about conditions that existed before the traditional Big Bang happened. We can measure properties of that pre-bang state. We can test theories about it. The universe keeps secrets, but it also leaves clues. The cosmic microwave background is the oldest light in the universe. Released 380,000 years after the Big Bang, it's been traveling through space for over 13 billion years. When we capture this ancient radiation with telescopes, we're seeing a snapshot of the cosmos when it was young, hot, and simple. But hidden within that snapshot is information from even earlier, from the inflationary epoch before the Big Bang. Here's how that works. During inflation, the vacuum energy dominating the universe had quantum properties. Like everything in quantum mechanics, it experienced random fluctuations. These weren't just tiny ripples. Inflation amplified them, stretching microscopic quantum jitters into variations spanning millions of light years. When inflation ended and the Big Bang transition occurred, those variations became imprinted on the distribution of matter and energy. Regions with slightly more density would eventually form galaxy clusters. Regions with slightly less density would become cosmic voids. The structure of the entire universe traces back to quantum randomness during inflation. The cosmic microwave background captures this information because the photons released 380,000 years after the Big Bang traveled through space that already had these density variations. Hot spots in the radiation come from regions that were slightly denser. Cold spots come from regions that were less dense. The pattern we see today is a fossilized map of conditions created during inflation. Scientists have measured this map with incredible detail. The temperature varies by only a few parts per 100,000. The universe was remarkably uniform even then. But within that uniformity lies structure. Specific sizes of hot and cold regions appear more frequently than others, creating what cosmologists call the power spectrum. Inflation makes precise predictions about what this power spectrum should look like. The distribution of fluctuation sizes should follow a nearly scale-invariant pattern, meaning fluctuations of different sizes have almost the same amplitude. Observations confirm this prediction. The match is so close that it's become one of the fundamental pillars of modern cosmology. But the cosmic microwave background reveals more than just density variations. It also carries information about polarization, the orientation of the electromagnetic waves. This polarization gets affected by gravitational waves, and inflation should produce gravitational waves as a byproduct of its exponential expansion. Detecting these primordial gravitational waves remains one of cosmology's biggest goals. If found, they would provide direct evidence of inflation's energy scale and offer a window into physics at temperatures far beyond what particle accelerators can reach. Multiple experiments are searching for this signal right now. Even without detecting gravitational waves yet, the temperature and polarization data we already have constrains inflation theories. Some models predict large gravitational wave signals. Those models are now ruled out. Other models predict specific patterns in how fluctuations behave on different scales. Observations test those predictions and eliminate models that don't match. The cosmic microwave background has become a laboratory for studying the pre-Big Bang universe. Every improvement in measurement technology brings new insights. The data keeps getting better, and the picture of inflation keeps getting clearer. What it reveals is a universe that existed in a state completely different from anything we experience today. We assume time flows in one direction, from past to future. We remember yesterday, but not tomorrow. Causes precede effects. The sequence of moments feels fundamental to reality, but what if time itself only began during inflation, or even later? This isn't wild speculation. It comes from taking Einstein's general relativity seriously. Einstein showed that time and space are linked as spacetime, a four-dimensional fabric that can bend, stretch, and warp. Gravity isn't a force acting through space and time. Gravity is the curvature of space-time itself. This means time is physical. It's part of the universe, not something external that the universe exists within. And if time is physical, then asking what happened before the universe existed might be like asking what's north of the North Pole. The question assumes a framework that doesn't apply. Stephen Hawking explored this idea using quantum mechanics. In collaboration with James Hartle, he proposed the no-boundary hypothesis. The mathematics describes the universe's origin using something called imaginary time, a concept from quantum theory, where time behaves like a spatial dimension. In this framework, the universe doesn't have a beginning point. Instead, it smoothly transitions from a timeless quantum state into the classical space-time we experience. Think of the surface of Earth. If you travel south, you eventually reach the South Pole. You can't go farther south because there is no farther south. Then you've reached the limit. The no-boundary proposal suggests something similar for time. Trace cosmic history backward, and you eventually reach a boundary where time itself curves back on itself. There's no before, because time doesn't extend in that direction. This creates a strange picture. The universe is finite in time, but has no beginning moment. It's self-contained, no creator needed, no violation of causality, no infinite past to explain. Other physicists disagree. Julian Barber argues that time is an illusion emerging from the changing configurations of matter. According to his view, only the present moment exists. The past is a memory stored in the current arrangement of particles. The future hasn't happened yet, so it doesn't exist. If time is illusory, then asking about before the Big Bang becomes meaningless in a different way. The confusing part is that both perspectives might be partially correct. At everyday scales, time behaves as we expect. Clocks tick. Causes produce effects. The arrow of time points clearly forward. But at the quantum scale governing the universe's origin, time becomes fuzzy and uncertain, just like position and momentum. During inflation, if it occurred, time likely existed in a conventional sense. The vacuum energy state could persist for a duration. Space could expand over time. But before inflation, that's where our understanding fails. The mathematical singularity at the beginning of time might be telling us that general relativity breaks down and a quantum theory of gravity is needed. Nobody has successfully combined quantum mechanics and general relativity into a complete theory yet. Without that theory, questions about the ultimate beginning remain open. We can trace cosmic history back to the Planck time, 10 to the negative 43 seconds after the Big Bang. Earlier than that, our physics doesn't work. What does before even mean in that regime? Language fails us when discussing the origin of time. Every word we use assumes time already exists. Before implies an earlier moment. Cause implies something happening first. Beginning suggests a transition from not existing to existing. But if time itself emerged with the universe, these concepts collapse into paradox. Cosmologists wrestle with this constantly. They need to communicate ideas that transcend normal experience, using words built for normal experience. The result can sound contradictory or confusing, but the confusion comes from the limits of language, not necessarily the limits of reality. One approach is to abandon the notion of before entirely. Georges Lemaitre, the Belgian priest and physicist who first proposed cosmic expansion, suggested that the universe began in a day without yesterday. Saint Augustine made a similar argument 1600 years earlier, claiming that time was created along with the universe, so asking what came before is nonsensical. Modern physics provides a framework for this. General relativity describes space-time as a manifold, ATT, a mathematical structure with definite boundaries. Time could have a boundary at the Big Bang, just as the surface of Earth has a boundary at the poles. Asking what's before the boundary is like asking what color is Tuesday. The question contains a category error. But here's where it gets interesting. Quantum mechanics might allow an escape from this conclusion. In quantum theory, particles can tunnel through barriers they shouldn't classically be able to cross. Electrons tunnel through insulators. Alpha particles tunnel out of atomic nuclei. It's a thoroughly confirmed phenomenon. Some physicists propose the universe itself tunneled into existence from a quantum vacuum state. Alexander Vilenkin developed this idea in detail. He describes a scenario where a universe with zero size has some small quantum probability of tunneling into a state with non-zero size. Once it makes that transition, inflation takes over and expands it to cosmic proportions. In this picture, there is no before in the usual sense, but there is a prior quantum state, the vacuum from which the universe tunneled. Time begins when the universe achieves classical space-time properties, but the quantum state exists outside of time as we know it. David Bohm's pilot wave interpretation of quantum mechanics offers another perspective. In Bohm's framework, particles have definite positions at all times, guided by a quantum potential. When applied to cosmology through the Wheeler-DeWitt equation, this suggests the universe could have definite properties even at the moment of creation. The quantum potential acts like an effective cosmological constant, driving the initial expansion. These ideas remain theoretical, but they point toward a resolution. Maybe before the Big Bang doesn't mean earlier in time. Maybe it means prior in some other sense, causally prior, or logically prior, or quantum mechanically prior. The state from which the universe emerged wouldn't exist at a moment before time began. It would exist outside the framework of time altogether. This challenges our intuition deeply. We're accustomed to thinking of existence as happening in time, but quantum states don't necessarily exist in time. They exist in configuration space, an abstract mathematical realm describing all possible states a system could occupy. The universe's emergence could be a transition from one configuration to another, with time itself being a feature that emerges during the transition. Philosophers have argued about these questions for millennia. Physics now gives us tools to make those arguments precise, testable, and grounded in observation. We may never have a complete answer, but we're asking better questions. And some theories go even farther. What if our universe wasn't born from nothing, but from a collision? What if everything we see came from two massive structures smashing together in a higher dimension? This is the ekpyrotic model, and it's built on serious mathematics. The theory emerges from string theory, CNA, a framework that describes particles as tiny vibrating strings rather than point-like objects. String theory requires extra dimensions beyond the three of space and one of time we experience. These dimensions could be curled up small, or they could be large but hidden from our direct perception. In some versions of string theory, our universe exists on a three-dimensional membrane, or brain, floating in higher dimensional space. Think of a sheet of paper existing in a three-dimensional room. We're trapped on the sheet, unable to move off it, while the room contains other dimensions we can't access. The ekpyrotic model, proposed in 2001 by physicists including Paul Steinhardt and Neil Turok, suggests there are two such brains parallel to each other. An attractive force pulls them together over vast spans of time. They approach slowly, then they collide. The collision releases enormous energy. From our perspective, trapped on one brain, this would look like the Big Bang. Matter and radiation flood our three-dimensional space. The universe heats up, expands, cools, and evolves into the cosmos we observe today. But it wasn't a beginning, it was a crash. This theory solves several problems that inflation struggles with. It explains why the universe is flat and uniform without requiring an exponentially fast expansion. The slow approach of the brain smooths out any irregularities before impact. It explains the pattern of fluctuations in the cosmic microwave background as vibrations created by the collision, and it avoids the multiverse problem that plagues inflationary models. Inflation, if it lasts long enough, produces an infinite number of pocket universes with random properties. This makes the theory hard to test because any observation can be explained as, we just happen to live in this pocket. The ekpyrotic model doesn't have this issue. One collision creates one universe with predictable properties, but the ekpyrotic scenario faces challenges. Nobody fully understands what happens during a brain collision. String theory isn't developed enough yet to precisely calculate the outcome. Some critics argue the collision might destroy the smoothness that the model depends on. Others point out that getting the right spectrum of density fluctuations requires fine-tuning the collision parameters. Despite these difficulties, the ekpyrotic model remains scientifically viable. It makes testable predictions. For example, it predicts gravitational waves from the collision would be too weak to detect in the cosmic microwave background. Inflation predicts they might be detectable. Future observations could distinguish between these scenarios. The ekpyrotic model also connects to something deeper, the idea that our Big Bang wasn't unique. If brains can collide once, they can collide multiple times. The collision could bounce the brains apart. They'd separate, drift in the higher dimension, then get pulled back together by the attractive force. Another collision, another Big Bang. This leads to a cyclic cosmology, where the universe goes through endless cycles of collision and separation. Each cycle creates a cosmos. Each cycle ends when the brains separate. Then, the process repeats. From our perspective, it would look like the universe expands, then contracts, then bounces into a new expansion. Except the bounce happens through a collision in a higher dimension, not a simple reversal of our three-dimensional space. The implications are staggering. The singularity at the beginning of the Big Bang has haunted physics for decades, a point of infinite density, infinite temperature, infinite curvature, a place where the equations break down and give nonsensical answers. Most physicists don't believe the singularity is real. They see it as a sign that general relativity fails under extreme conditions. The Big Bounce theory offers a solution. Instead of the universe beginning at a singularity, it transitions smoothly from a contracting phase into our current expanding phase. The bounce happens at a finite, though extremely high, density. No infinities, no breakdown of physics. This isn't just wishful thinking. It's grounded in loop quantum gravity, AI, an approach to combining quantum mechanics and general relativity. In loop quantum gravity, space itself has a discrete structure at the tiniest scales, like pixels on a screen. When you try to compress matter and energy into an infinitely small point, the quantum properties of space prevent it. There's a minimum volume, A bounce becomes inevitable. Calculations using loop quantum gravity show that a collapsing universe would reach a maximum density, then rebound into expansion. The mathematics is complex, but the conclusion is clear. Quantum effects create a repulsive force at extreme densities that overwhelms gravity. Think of it like compressing a spring. Push too hard, and it pushes back. Recent work published in 2020 by Robert Brandenberger and Ziwei Wang explored how a bounce could produce the observed features of our universe. They found that if the pre-bounce universe underwent a period of slow contraction, similar to inflation but in reverse, it could generate the same pattern of density fluctuations we see in the cosmic microwave. Background: this means the universe before the bounce might have looked like ours in reverse. Galaxies merging instead of separating, light shifting toward blue instead of red, time running backward from our perspective, though forward from the perspective of observers living in that epoch. When the bounce occurred, information from the pre-bounce universe could have survived the transition. The fluctuations in matter and energy distributions would carry through, seeding structure in the post-bounce cosmos, our cosmos. This creates a radical picture. The Big Bang wasn't the start. It was the midpoint of a much longer story. Before our expansion came a contraction. Before that, possibly another expansion. The universe might be far older than 13.8 billion years. It might have no age at all, stretching infinitely into the past through endless cycles. The Big Bounce avoids many philosophical problems that plague creation from nothing scenarios. It doesn't require explaining why the universe exists rather than nothing. It doesn't require a moment when time begins. It simply requires quantum gravity to behave the way loop quantum gravity predicts. Testing this theory is challenging. The bounce itself happened under conditions we can't reproduce in laboratories. But the theory makes predictions about the cosmic microwave background and the spectrum of gravitational waves that might be detectable. Several experiments are searching for these signatures. If the Big Bounce is correct, then the question shifts. We don't need to explain the origin of the universe. We need to explain its structure and its cycles. Which brings us to the most ambitious idea yet. Imagine a cosmos that never began and never ends. A universe caught in an eternal rhythm of expansion, contraction, bounce, and expansion again. Each cycle lasting trillions of years. Each cycle creating the conditions for stars, planets, and possibly life. This is cyclic cosmology. The idea isn't new. Ancient Stoic philosophers proposed an eternal cycle of cosmic creation and destruction they called ekpyrosis. Hindu cosmology describes similar cycles over vast timescales, but modern physics puts these concepts on firm mathematical ground. In the cyclic model developed by Paul Steinhardt and Neil Turok, dark energy plays a crucial role. Remember, dark energy is the mysterious component causing our universe's expansion to accelerate. In their model, dark energy eventually pushes galaxies so far apart that the universe becomes essentially empty. Matter gets diluted to negligible density. Stars burn out. Black holes evaporate through Hawking radiation over incomprehensible time spans. But the dark energy doesn't disappear. It continues to exist, and in the ekpyrotic cyclic model, it acts as a bridge to the next cycle. The same attractive force between brains that caused our Big Bang collision continues to operate. Over trillions of years, it pulls the brains together again. Another collision occurs. Another Big Bang erupts. A new universe begins. Crucially, each cycle doesn't produce identical conditions. The universe grows larger with each iteration. The scale factor, a measure of cosmic size, increases exponentially from cycle to cycle. Entropy builds up, but it gets diluted by the expansion. The second law of thermodynamics isn't violated because the universe keeps getting bigger, giving entropy more room to spread out. This solves the entropy problem that killed earlier cyclic models. In the 1930s, physicist Richard Tolman showed that a naively cyclic universe would accumulate entropy until it couldn't bounce anymore. The Steinhardt-Turok model avoids this by incorporating dark energy and allowing the universe to expand net over many cycles. Another cyclic proposal comes from Roger Penrose, the Nobel laureate mathematician. His conformal cyclic cosmology suggests the universe expands forever until all matter decays into radiation. At that point, nothing remains with a rest mass. Everything moves at the speed of light. When nothing has mass, the concepts of time and distance become meaningless. Penrose argues this massless state can be mathematically mapped onto a new Big Bang. The infinite future of one universe becomes the Big Bang of the next. It's conformal because the geometry is preserved under this transformation. Even though scales change, time becomes circular, or perhaps spiral. These models remain speculative, but they're testable. They predict specific patterns in the cosmic microwave background. Some versions predict we might see circular patterns from collisions in the previous cycle, like ripples on a pond imprinted in the radiation. Searches have been conducted. So far, no definitive signals found, but the search continues. Cyclic cosmology offers philosophical appeal. It removes the awkward question of why the universe exists. It always has existed and always will, changing form but never truly beginning or ending. Existence becomes fundamental, while specific configurations, like our current expanding universe, become temporary phases. But it also raises new questions. If cycles repeat forever, have there been infinite cycles? Does the universe have a memory of earlier cycles? Are the laws of physics the same in each cycle, or do they evolve? We may be on the verge of answering some of these questions. Here's a possibility that sounds like science fiction, but emerges from serious theoretical work. Each cycle of the universe might operate under different physical laws. The constants that govern particle masses, force strengths, and cosmic behavior could shift from one cycle to the next. Why would this happen? In many theoretical frameworks, the values of physical constants aren't set by fundamental principles. They're environmental, determined by how quantum fields settle into their lowest energy states. It's like water freezing. The exact pattern of ice crystals depends on random fluctuations during the freezing process. During a bounce or brane collision, the extreme energies could reset these fields. As the new universe expands and cools, the fields would settle into new configurations, different constants, different physics, a cosmos that looks and behaves differently from ours. This has profound implications. In most cycles, the constants might not allow complex structures to form. Galaxies wouldn't assemble, stars wouldn't ignite, chemistry might not exist. Those universes would be sterile, simple, and short-lived. But occasionally, by random chance, the constants would align just right. Atoms could form, complexity could emerge, life might evolve. We find ourselves in one of those rare, successful cycles because we couldn't exist in any other kind. This is a version of the anthropic principle, the observation that the universe must be compatible with the conscious life that observes it. In a cyclic multiverse, where each cycle has different physics, the anthropic principle explains our particular set of constants without requiring fine-tuning. Some physicists find this explanation unsatisfying. It replaces the mystery of why our constants have life-permitting values with the assumption that all possible values occur somewhere in the cyclic sequence. You haven't really explained anything, you've just moved the mystery one level deeper. Others embrace it. If the cyclic model is correct and constants vary between cycles, then we can make statistical predictions. We should find ourselves in a typical life-permitting cycle, not a maximally life-permitting one. Our universe should be close to the boundary, where complex structures barely form. Too far from the boundary would be statistically unlikely. Some evidence tentatively supports this. The cosmological constant in our universe sits uncomfortably close to the maximum value that would allow galaxies to form. Much larger and cosmic expansion would have accelerated so fast that matter could never clump together. Much smaller, and we'd need to explain why it's not exactly zero. We seem to be near a boundary, which cyclic anthropic reasoning predicts. Testing whether constants varied in previous cycles is nearly impossible. The bounce erases most information, but some theories suggest subtle imprints might survive. Topological defects, many, certain kinds of knots in spacetime, could potentially persist through a bounce and leave detectable traces. More realistically, we can test whether the framework allowing variable constants makes sense. String theory, for example, predicts a vast landscape of possible vacuum states, each with different effective laws of physics. Exploring which of these states are accessible and how transitions between them might occur is active research. The big picture, emerging from cyclic cosmology with variable physics, is humbling and grand simultaneously. Our universe isn't special. It's one outcome of an eternal process that generates cosmos after cosmos, most of them failures, some of them interesting, a few of them giving rise to observers who can ask these questions. We're left with a vision of reality far stranger than the simple something from nothing narrative. There might be no ultimate beginning, no final end, no single set of physical laws, just an infinite churning of possibilities, with brief windows where complexity flourishes before collapsing back into simplicity, then re-emerging in a new form. The universe, in this view, is not a creation, but an eternal transformation. General relativity and quantum mechanics are the two pillars of modern physics. General relativity describes gravity, black holes, and cosmic expansion. Quantum mechanics governs atoms, particles, and the microscopic world. Both theories work brilliantly in their domains, but they contradict each other at extreme scales. Loop quantum gravity attempts to resolve this conflict by applying quantum principles to space and time themselves. Instead of treating space as a smooth continuum, loop quantum gravity describes it as a network of discrete loops, tiny quantum units connected like chainmail. At normal scales, this discrete structure averages out and space appears smooth, just like a television screen, looks continuous from a distance, but is actually made of pixels. The key insight comes when you apply these ideas to the Big Bang singularity. In classical general relativity, matter collapses to infinite density, but loop quantum gravity says space has a minimum volume. You can't compress something smaller than the fundamental quantum unit of space, which exists at the Planck scale, about 10 to the negative 35 meters. When a collapsing universe reaches this density, quantum repulsion kicks in. The mathematics shows that gravity effectively reverses, becoming repulsive instead of attractive. The collapse halts and reverses into an expansion. The singularity gets replaced by a bounce, a smooth quantum bridge connecting contraction to expansion. This isn't speculation. Scientists have performed detailed calculations using loop quantum gravity equations. They've simulated how a universe evolves through the bounce. The results show that cosmological perturbations, the tiny fluctuations that seed galaxies, can propagate through the bounce without being destroyed. Information survives the transition. Abhay Ashtekar and his collaborators at Penn State have led much of this research. They've shown that a pre-bounce universe undergoing slow contraction would generate a nearly scale-invariant spectrum of perturbations, matching what we observe in the cosmic microwave background. The bounce doesn't erase this structure, it preserves it. This creates a testable prediction. Loop quantum gravity bounces should produce specific signatures in gravitational waves. The spectrum should differ slightly from what inflation predicts. As gravitational wave detectors become more sensitive, they might distinguish between these scenarios. There's also a philosophical shift here. Loop quantum gravity doesn't require anything beyond known physics. It doesn't invoke extra dimensions, colliding brains, or exotic forms of matter. It simply takes quantum mechanics seriously at all scales, including space-time itself. The singularity that terrified physicists for decades disappears. It was never real, just an artifact of using classical equations where they don't apply. Once you account for quantum effects, the universe has no beginning or end in the traditional sense. It's a continuous process with phases of expansion and contraction connected by quantum bridges. This resolves the paradox of creation. You don't need to explain how something came from nothing because there was never nothing. There was always a quantum space-time structure, eternally transforming between different states. But what triggered our particular phase? One of the strangest ideas in cosmology sounds like circular logic, but might be true. The universe could have created the conditions that allowed it to exist. It bootstrapped itself into reality through a self-consistent loop. Here's how this works. In quantum mechanics, the future can influence the past through what's called retrocausality. When you measure a particle's state, you don't just observe what it is, you retroactively determine what it was. The act of measurement reaches backward in time and selects which possibility becomes real from a cloud of quantum probabilities. John Wheeler, one of the great physicists of the 20th century, proposed that the universe might work the same way. He called it the participatory anthropic principle. The existence of observers who can measure and understand the universe contributes to bringing that universe into existence. The cosmos creates observers who look back at its origin and, through that observation, help define what the origin was. This sounds mystical, but it emerges naturally from certain interpretations of quantum mechanics. The universe's wave function describes all possible configurations it could have. When conscious observers emerge and begin making measurements, they collapse parts of this wave function, selecting which history actually occurred. In this view, the Big Bang wasn't just a random event. It was the only event consistent with a universe that would eventually produce observers. Other possible initial conditions might have led to sterile universes with no complexity. Those branches of the wave function never got actualized because no observers existed to collapse them into reality. This creates a causal loop. The universe exists in a form that allows observers. The observer's existence retroactively selects the initial conditions that led to them. The initial conditions cause the observers. The loop is self-consistent. Physicist James Hartle has explored these ideas mathematically. His work with Stephen Hawking on the no-boundary proposal incorporates this self-selection principle. The universe doesn't have a single fixed past. It has a superposition of possible pasts, and the act of existing in the present helps determine which past becomes real. Other frameworks reach similar conclusions through different routes. In Lee Smolin's cosmological natural selection, universes that produce black holes create baby universes through quantum tunneling. Each baby universe has slightly different physical constants. Over many generations, this process selects for universes optimized to produce black holes, which also happen to be good at producing stars, planets, and complexity. We exist in such a universe, not by chance, but because only this type of universe can persist through the selection process. The universe bootstraps its own existence through an evolutionary mechanism spanning across cosmic generations. These ideas remain controversial and difficult to test, but they point toward a resolution of the deepest mystery. Why is there something rather than nothing? The answer might be that nothing is unstable in a quantum framework. Any fluctuation that creates something which can sustain itself will persist. Others collapse. We observe a self-sustaining configuration because non-sustaining ones don't produce observers. The universe exists because it can exist. The conditions that make it possible are the conditions it selects for through its own evolution. Reality is a strange loop that creates itself, and the mathematics describing this gets even stranger. We experience 3 dimensions of space: left-right, forward-backward, up-down. Add time, and you get 4 dimensions. String theory says there are at least 7 more hidden dimensions, giving a total of 11. Why haven't we noticed them? The theory proposes they're compactified, curled up so small that we can't perceive them. Imagine an ant walking on a telephone wire. From far away, the wire looks one-dimensional. The ant can only move forward or backward, but up close, the wire has thickness. The ant could walk around its circumference, exploring a second dimension we initially missed. The extra dimensions in string theory work similarly. They exist at every point in our three-dimensional space, but they're rolled up at scales far tinier than atoms. Particles can vibrate through these hidden dimensions, and different vibration patterns appear to us as different particle types. An electron is one vibration mode, a quark is another. Photons, neutrinos, everything emerges from strings, vibrating through this higher dimensional space. This framework has profound implications for cosmology. Our universe might be a three-dimensional surface embedded in this higher dimensional space. Everything we see, stars, galaxies, light, is trapped on this surface. But gravity is different. Gravitational effects can leak into the extra dimensions, which might explain why gravity is so much weaker than the other fundamental forces. The ekpyrotic model we discussed earlier exploits this. If parallel three-dimensional branes exist in the higher dimensional bulk, and if they can move through those extra dimensions, then collisions become possible. Our Big Bang would be the aftermath of such a collision, with the pre-collision state existing in this higher dimensional framework. String theory also suggests that different compactifications of the extra dimensions produce different physical laws. There might be 10 to the 500 or more distinct ways to curl up the extra dimensions, each creating a different vacuum state with different particle masses and force strengths. This vast landscape of possibilities connects to the idea of varying constants between cosmic cycles. Testing these ideas is extraordinarily difficult. The energies needed to probe the extra dimensions directly exceed anything achievable in particle accelerators by many orders of magnitude. But indirect evidence might exist. Gravitational waves propagating through the bulk could carry signatures of extra dimensions. Tiny deviations in how gravity behaves at small scales might reveal the geometry of hidden dimensions. Experiments at the Large Hadron Collider search for signs of extra dimensions by looking for missing energy in particle collisions. If particles escaped into the bulk, energy would seem to disappear. So far, no definitive signals, but the search continues at higher energies and with greater precision. String theory remains incomplete and controversial. Some physicists embrace it as the best candidate for a theory of everything. Others criticize it for making few testable predictions and requiring fine-tuning to match observations. The debate continues, but the core insight persists. The universe we observe might be a shadow of a larger reality. The three dimensions of space we navigate might be an illusion, a projection of something far more complex existing in realms we can't directly access. This raises a question about the pre-Big Bang state. If extra dimensions exist, what role did they play in the universe's origin? Inflation was supposed to be a one-time event, a brief period of exponential expansion that set up our Big Bang, then ended. But the mathematics suggests something far stranger. Once inflation starts, it might never completely stop. Here's why. Inflation is driven by a quantum field called the inflaton. When this field sits at a high energy value, space expands exponentially. As the field rolls down toward lower energy, inflation slows and eventually stops. The field's energy converts to matter and radiation. That's the Big Bang we know. But quantum fluctuations affect the inflaton field, just like they affect everything else. In some regions of space, random fluctuations push the field back up to higher energy before it can finish rolling down. Those regions keep inflating. Meanwhile, other regions successfully end inflation and produce hot Big Bang conditions. This creates a fractal structure. Our observable universe is a pocket where inflation ended, but beyond our cosmic horizon, other regions are still inflating. And within those inflating regions, New pockets constantly form where inflation stops. Each pocket becomes a Big Bang universe. Each one expands, cools, and potentially develops galaxies, stars, and life. The process never ends. Inflation continues eternally in the background, spawning an infinite number of pocket universes. Alan Guth and Andre Linde developed this eternal inflation framework in the 1980s. It's a natural consequence of combining inflation with quantum mechanics. The implications are staggering. There's not one universe, there's a vast, possibly infinite multiverse. Our Big Bang is just one bubble in an endless foam of universes. Each bubble might have different properties. The quantum fluctuations that create new pockets could also affect the values of physical constants, producing pocket universes with different laws of physics. This resolves some mysteries while creating others. It explains why our universe has life-permitting constants. There are infinite universes with all possible constants. We necessarily find ourselves in one compatible with our existence. But it also means the theory can't predict what we should observe, because every possible observation occurs somewhere in the multiverse. Eternal inflation also has a past. The Borda-Guth-Vilenkin theorem, proved in 2003, shows that any region of space, expanding on average, must have a boundary in the past. Inflation can't be eternal into the past. It must have started somehow, from some initial condition. This brings us back to the origin question. What triggered inflation in the first place? The metastable false vacuum? A quantum fluctuation? A prior contracting phase? The theorem doesn't tell us what came before, but it proves there was a before. Some physicists find eternal inflation disturbing. It seems to make science impossible if every outcome exists somewhere. Others argue we can still make probabilistic predictions by counting which types of observers are most common across the multiverse. The debate is unresolved, but the mathematics of eternal inflation is solid. Unless quantum mechanics or the inflaton field behaves very differently than we think, the multiverse seems unavoidable. What does this mean for the concept of nothing? Stand back and look at the big picture. If eternal inflation is correct, reality is not a single universe with one Big Bang. It's an infinite collection of disconnected regions, each with its own Big Bang, expanding within an ever-inflating background. Think of it as quantum foam on a cosmic scale. The inflating space is the substance. The pocket universes are bubbles forming within it. Each bubble thinks it's the entire universe because the inflating background expands faster than light, forever hiding other bubbles beyond an unreachable horizon. This structure might be nested. Within each pocket universe, if conditions allow, new phases of inflation could begin. Those would spawn their own sub-pockets. You'd get a hierarchy of nested realities, each level spawning the next, all embedded within the eternal inflation that never stops. Max Tegmark has classified different types of multiverses. Level 1 is simply distant regions of our own universe, beyond our observation horizon but obeying the same physics. Level 2 is the eternal inflation multiverse we're discussing. Different bubbles with potentially different physical constants. Level 3 involves the many worlds interpretation of quantum mechanics, where every quantum measurement splits reality into branches. Level 4 would be completely different mathematical structures obeying different logical rules. The Level 2 multiverse from eternal inflation is the most scientifically grounded. It emerges directly from combining well-tested physics, general relativity, quantum mechanics, and inflation. You don't need to assume anything exotic. The multiverse is a consequence, not an assumption, but it creates an observability problem. We can only see inside our bubble. The inflating background between bubbles expands so fast that light from other bubbles can never reach us. They're not just far away, they're causally disconnected. No information can travel between bubbles. Each pocket universe is fundamentally isolated. This seems to put other bubbles beyond the reach of science. If we can't observe them, test predictions about them, or interact with them in any way, Are they really scientific entities, or have we crossed into metaphysics? Some argue the multiverse remains scientific because it's a prediction of testable theories. We don't test the multiverse directly, we test inflation. If inflation is correct, eternal inflation follows naturally. Rejecting the multiverse means rejecting the logical consequences of confirmed physics. Others remain skeptical. They argue that good scientific theories should make definite predictions about what we observe. The multiverse allows anything, which means it predicts nothing. It's a failure of our theories, not a feature of reality. The debate continues, but observationally, we're stuck in our bubble. We can study its properties. We can map the cosmic microwave background. We can measure the expansion rate and the dark energy density. All of this tells us about our pocket universe. Whether infinite other pockets exist remains unknown, but the mathematics strongly suggests they do. And if they do, then the question of what existed before the Big Bang gets even stranger. Our Big Bang was not the beginning of inflation. It was the end of inflation in our local region. Other regions never stopped inflating. Still others ended inflation earlier or later. There's no universal before the Big Bang. Each pocket has its own timeline, its own origin, its own history. The multiverse as a whole might be timeless, with pockets beginning and ending at all moments, embedded in an eternal background. This is the picture modern cosmology paints. Not a simple creation story, a complex, layered reality where our universe is one small piece. For decades, popular science treated the Big Bang singularity as a physical reality, a point where the universe was infinitely dense, infinitely hot, infinitely curved. But physicists never believed it. A singularity signals the breakdown of your theory, not a description of reality. When equations give infinite answers, they're telling you the mathematical framework no longer applies. You've pushed the model beyond its domain of validity. General relativity predicts singularities. Black holes have them at their centers. The Big Bang has one at its beginning. But general relativity is a classical theory. It doesn't include quantum mechanics. At small scales and high energies, quantum effects become crucial. Ignoring them guarantees your predictions will fail. Think of it like predicting the behavior of water. Classical fluid mechanics works great for describing rivers, waves, and pipes. But at molecular scales, where individual water molecules matter, you need quantum chemistry. Classical fluid equations give nonsensical results at atomic scales because they're the wrong tool. General relativity is the wrong tool at Planck scales. The Planck length is 10 to the negative 35 meters. The Planck time is 10 to the negative 43 seconds. The Planck energy is about 10 to the 19 GeV, roughly the energy of a flying mosquito compressed into a single particle. These are the scales where quantum gravity becomes essential. At these scales, space and time stop behaving classically. They fluctuate, they become uncertain. The very concepts of distance and duration lose their usual meanings. A singularity, which requires compressing something into exactly zero volume, becomes impossible. Quantum mechanics won't allow it. Stephen Hawking and Roger Penrose proved theorems showing that general relativity predicts singularities under very general conditions. Their work was brilliant and important, but it also highlighted exactly where general relativity fails. The singularity theorems tell us where we need a better theory. Loop quantum gravity replaces the singularity with a bounce. String theory might replace it with a minimum size determined by string length scales. Other quantum gravity proposals have their own solutions. The details differ, but the conclusion is the same. The singularity isn't real. This means the Big Bang wasn't a moment when the universe sprang from nothing into something. It was a transition from one quantum state to another. The pre-transition state might have been a contracting universe, an inflating vacuum, a higher dimensional brain configuration, or something else entirely. But it was something, not nothing. The mathematical fiction of the singularity misled generations of physicists and the public. It made the origin of the universe seem more mysterious than it is. Yes, we don't fully understand quantum gravity. Yes, the precise details of the transition remain unclear, but we know the universe didn't begin at an infinitely dense point, because infinite density is unphysical. This shifts the question. We're not trying to explain how something came from absolute nothing. We're trying to explain what the pre-Big Bang quantum state was and why it transitioned into our current expanding universe. That's still a profound question, but it's a tractable one. Quantum mechanics and general relativity are both experimentally confirmed to incredible precision. Quantum mechanics predicts the behavior of atoms, lasers, and computer chips with perfect accuracy. General relativity predicts the orbits of planets, the bending of light around galaxies, and the detection of gravitational waves. Both theories work flawlessly in their domains, but they contradict each other when you try to combine them. This isn't a minor technical issue. It's a fundamental clash of principles. In quantum mechanics, you can measure a particle's energy with arbitrary precision if you're willing to wait long enough. Time is a background parameter that flows uniformly. In general relativity, time is part of space-time, which curves and warps. Time runs at different rates, depending on gravity and motion. There's no universal clock. In quantum mechanics, particles exist in superpositions. An electron can be in multiple places at once until you measure it. In general relativity, space-time has a definite geometry. You can't have space-time in a superposition of different curvatures. Or can you? These contradictions become critical at Planck scales, where both quantum effects and gravitational effects are strong. You need a theory of quantum gravity, N1, a framework that incorporates both sets of principles consistently. Nobody has one yet that's complete, tested, and universally accepted. String theory offers one approach. It replaces point particles with vibrating strings. This smooths out the singularities that plague quantum gravity calculations. The mathematics is elegant, and the theory potentially describes all forces and particles within one framework, but it requires extra dimensions, has many possible solutions, and makes few testable predictions at accessible energies. Loop quantum gravity takes a different route. It quantizes spacetime directly, treating it as a network of discrete loops. This avoids singularities and explains how space emerges from quantum building blocks. But it struggles to incorporate matter and forces beyond gravity. Connecting it to particle physics remains challenging. Other approaches exist. Causal dynamical triangulations build spacetime from simple geometric pieces and evolve it through quantum rules. Asymptotic safety suggests gravity might remain well-behaved at high energies through a special mathematical property. Emergent gravity theories propose that spacetime isn't fundamental, but emerges from more basic quantum information. Each approach has strengths and weaknesses. Each makes different predictions about Planck scale physics. And frustratingly, directly testing these predictions is nearly impossible with current technology. The energies are too high, the scales are too small, but cosmology provides an indirect testing ground. The early universe naturally probed Planck-scale physics. If we can decode the messages written in the cosmic microwave background, in the spectrum of gravitational waves, in the distribution of large-scale structure, we might distinguish between competing quantum gravity theories. This is why understanding what happened before the Big Bang matters scientifically. It's not just philosophical curiosity, it's a window into the most fundamental laws of physics. The origin of the universe is the one natural laboratory where quantum gravity was fully operational, leaving fingerprints we can potentially read. The battle between quantum mechanics and general relativity will be resolved. When it is, we'll have a complete picture of how space-time and matter work at all scales. And with it, we'll understand what nothing really means in the deepest sense. One equation might hold the key. In 1967, John Wheeler and Bryce DeWitt derived an equation that attempts to describe the quantum state of the entire universe. It's deceptively simple looking, but it contains profound implications for cosmology and the question of origins. The Wheeler-DeWitt equation treats the universe's geometry and matter content as quantum variables. Just as an electron has a wave function describing its possible positions, the universe has a wave function describing its possible configurations. The equation tells you how this wave function evolves, not in time, but in terms of relationships between different geometries. Here's the strange part. The equation doesn't contain time. There's no variable representing when things happen. Instead, it describes correlations between different aspects of the universe's state. It's sometimes called the equation with no time, and it raises deep questions about whether time is fundamental or emergent. When applied to cosmology, the Wheeler-DeWitt equation allows solutions where a universe tunnels into existence from a state with zero size. This isn't a metaphor. It's a quantum mechanical process, similar to how particles tunnel through barriers. The universe starts in a configuration that classically couldn't expand. Then, quantum tunneling allows it to jump to a configuration that can. Alexander Vilenkin developed this universe from nothing scenario using the Wheeler-DeWitt equation. In his framework, the nothing is a quantum vacuum state with no classical spacetime. The universe tunnels from this state into a small, closed space that immediately begins inflating. From our perspective inside the universe, it looks like time begins at the moment of tunneling, but calling it nothing is misleading. The quantum vacuum state exists. It has properties. It's described by mathematical laws. It's not absolute philosophical nothingness. It's the quantum mechanical ground state before classical spacetime emerges. Other solutions to the Wheeler-DeWitt equation exist. The Hartle-Hawking no-boundary proposal uses imaginary time to smooth out the singularity. Bohm's pilot wave interpretation suggests the quantum potential in the equation acts like an effective cosmological constant. Each approach gives different insights into what the pre-classical state might be. Chinese physicists Dongshan He, Dongfeng Gao, and Qingyu Kai published work in 2014 exploring spontaneous creation solutions. They showed that under certain conditions, a Planck-sized vacuum bubble has a non-zero quantum probability of expanding rather than collapsing. Once expansion begins, inflation takes over and creates a universe. The probability is tiny. But in a timeless quantum realm, where all possibilities exist in superposition, tiny probabilities become actual outcomes given enough trials. And in an eternal quantum foam of fluctuating vacuum states, every possibility eventually happens. This provides a mechanism for the universe's origin that doesn't require an external cause. The quantum vacuum is inherently unstable. Virtual fluctuations constantly occur. Most collapse immediately. But occasionally, by chance, one grows into an inflationary bubble that becomes a universe. The Wheeler-DeWitt equation is not a complete theory. It assumes a particular form of quantum mechanics and doesn't incorporate all aspects of quantum field theory. But it demonstrates that mathematics allows for spontaneous creation of universes from quantum states. Whether nature actually uses this mechanism remains unknown. Testing these ideas is extraordinarily difficult. The wave function of the universe isn't directly observable. We're inside it, part of it. We see its consequences, the structure of spacetime, the distribution of matter, but not the underlying quantum state itself. Yet, the implications are clear. The universe's origin might be a quantum event requiring no external trigger. The laws of physics themselves might be sufficient to explain existence. Step back from the details and look at the landscape of theories. Inflation before the Big Bang, cyclic bounces, ekpyrotic collisions, eternal inflation multiverse, Wheeler-DeWitt quantum tunneling, loop quantum gravity bridges. Each framework is different, but they share a common theme. None of them require an absolute beginning. The Big Bang was a transformation, not a creation. Before it came, something else, whether inflationary vacuum, contracting universe, quantum foam, or colliding brains. And before that, possibly something else still. The chain of causation might extend infinitely into the past, with no first cause, no moment of creation, no start to time. This challenges our intuition. We're accustomed to stories with beginnings, birth, genesis, first moments. But nature doesn't care about human narrative preferences. If the mathematics says time is eternal, then it's eternal. Alternatively, time might be cyclic or even illusory. Roger Penrose's conformal cyclic cosmology suggests the infinite future of one cosmic epoch becomes the Big Bang of the next. Time loops back on itself. Julian Barber argues time is an emergent property of changing configurations, not a fundamental dimension. Different perspectives, but both suggest linear time with a definite start is naive. The philosophical implications are profound. If the universe has no beginning, then asking why it exists becomes strange. It exists because it always has existed in some form. Existence is the default state, not something that needs explaining. Nothingness would require an explanation. Why wouldn't quantum fluctuations, vacuum energy, or space-time curvature exist? This reverses the usual framing. We've assumed nothingness is simpler than something, so existence needs justification. But in physics, empty quantum states are highly constrained. True nothingness, i.e., no fields, no vacuum energy, no quantum fluctuations, no mathematics, no laws, might be impossible. It might violate consistency requirements we don't fully understand yet. If so, then something has always existed and always will exist. The universe transforms continuously. It goes through phases, expanding, contracting, bouncing, inflating, generating structure, dissipating into radiation, repeating. Each phase looks different, but the underlying reality persists. We find ourselves in an expanding phase seeded by a hot Big Bang that was itself seeded by cold inflation. Trillions of years from now, dark energy might dominate completely, diluting matter to negligible density. The universe would become cold and empty again. Is that an end? Or just another phase transition preparing the conditions for what comes next? If brains collide, another Big Bang could occur. If quantum tunneling happens, new inflationary bubbles could spawn. If loop quantum gravity is correct, maximum density could trigger a bounce. The universe would continue, just in different form. This picture fits with deeper principles in physics. Energy is conserved. Information might be conserved. Fundamental constants seem to be constant. Reality has structure and follows rules. Why would that structure suddenly appear from nothing or disappear into nothing? The universe doesn't begin or end. It transforms. And that transformation is governed by principles we're gradually uncovering through observation, experiment, and mathematical reasoning. The question shifts from why is there something rather than nothing to what determines the form that something takes at any given moment. The answer to what existed before the Big Bang is both simpler and stranger than absolute nothing. There was something, a quantum state, a vacuum field, a contracting universe, a colliding brain, a timeless configuration space. The details remain uncertain. The framework differs between theories, but the conclusion is consistent. Nothing, in the philosophical sense, never existed, and possibly cannot exist. The quantum vacuum won't allow it. The uncertainty principle prevents it. The mathematics forbids it. Reality, at its deepest level, is not empty. It's not static. It's a dynamic system of fields and probabilities and geometry that never stops evolving. The Big Bang was one moment in this endless evolution, an important moment for us, because it created the conditions for stars, planets, and life. but not a special moment cosmically, just a transition, like water turning to steam, except what transitioned was space-time itself. Modern cosmology has pushed our understanding back beyond the traditional Big Bang to reveal a richer story. We know inflation happened first, driven by vacuum energy. We know the universe might be cyclic, bouncing, or colliding through endless epochs. We know quantum gravity replaces the singularity with something finite. We know the vacuum contains energy that shapes cosmic evolution. What we don't know yet is which framework is correct. Is it ekpyrotic collisions, loop quantum bounces, eternal inflation multiverse, Vilenkin tunneling? Perhaps multiple frameworks are correct in different regimes. Perhaps they're all approximations of a deeper theory we haven't discovered. Future observations will narrow the possibilities. Better measurements of the cosmic microwave background, detection of primordial gravitational waves, more precise tests of dark energy, advances in quantum gravity theory, experiments pushing to higher energies. Each piece of data constrains what models are viable, but already we know enough to revolutionize how we think about origins. The universe didn't come from nothing. It came from something that transforms. That something has always existed, at least as far as our physics can tell. The question isn't why existence rather than non-existence. The question is why this particular form of existence right now. And the answer involves quantum mechanics, gravity, vacuum energy, inflation, and possibly higher dimensions. It involves mathematics, describing how fields evolve, how space-time curves, how probabilities collapse into actuality. It involves natural law, not supernatural intervention, physical process, not metaphysical mystery. The cosmos is not a creation. It's an eternal pattern of change, sometimes expanding, sometimes contracting, sometimes inflating, sometimes bouncing, always transforming, always existing, never truly beginning or ending in any absolute sense. We're part of this transformation, temporary arrangements of atoms, assembled by the cooling aftermath of one particular Big Bang in one particular region of an infinite multiverse, or one particular cycle of an eternal recurrence. We exist for a brief moment, aware and curious, trying to understand the larger pattern we're embedded in. And what we've learned is humbling. The universe is far older, far larger, and far stranger than we imagined. Our Big Bang wasn't the start of everything. It was barely even a start. Just one more transition in a reality that has no beginning and needs none. Nothing never existed. The void was never empty. Reality is eternal transformation, and we're fortunate enough to witness one brief phase of it. That's what existed before the Big Bang. That's what exists now. That's what will exist forever. Not nothing, everything.